Guys, welcome back to another video. In today's video, I'm going to be going over limits at infinity. So let's begin. Limits at infinity essentially covers the end behavior of a function that exists on an interval. So by definition, a limit at infinity describes the value that a function approaches as x grows very large in magnitude. So in this picture to the left, these symbols indicate that the limit at positive and negative infinity exists and is equal to L. So the limit as x approaches negative infinity of f of x is equal to L, and the limit as x approaches infinity of f of x is equal to L. So essentially it says that the limit exists and is equal to L. So let's say we have a graph that looks like this, and this is towards infinity, this is towards negative infinity. Let's say that the value that approaches here is L, and the value that also approaches here is L. So that's basically what the limit means. So it approaches a value L. So this is an example of what a function approaches as x approaches infinity. Over here, we have the function f of x is equal to 5x squared over x squared plus 1. And we're going to find the limit of this function as x approaches infinity. So we're going to look for the right side of the graph as it approaches infinity. So if you were to plug in some x values, we get that x equals 1 is equal to 2.5, x equal to 10 is equal to 4.95, x equal to 100 is equal to 4.995, and x equal to 1000 is equal to 4.99995, and that infinity is equal to 5. So as we can see from the values plugged in, as we approach infinity for the x values, the function will approach 5, which is what is shown here in the graph. So let's find the limit of f of x as x approaches infinity. So basically, as the graph of 5x reaches infinity, it will grow and grow without bound. So let's plug in like f of 10. F of 10 is equal to 50. F of 100 is equal to 500. F of 1000 is equal to 5000. F of 1 million is equal to 5 million, and so on. So as you plug in larger and larger values of x, the function will approach infinity. So the limit here is equal to positive infinity because it's constantly growing and growing and growing as you increase the x inputted into it. So now we're going to find the limit of f of x as x approaches infinity of the function f of x is equal to 1. So since the function f of x is equal to 1 is constant, it does not change at all across its domain, which means that the limit as it approaches infinity will just be 1 because it's not changed at all and it stays constant. So no matter what you input into here, like let's say we have f of 100, it's still going to be equal to 1. F of 2 million is still going to be equal to 1. So that's going to be our answer. So now let's talk about the definition of a horizontal asymptote. A horizontal asymptote is a horizontal line y equals L that a graph approaches as x goes to positive infinity or negative infinity. So if the limit as x approaches positive infinity of f of x is equal to L, then the line y equals L is a horizontal asymptote. If the limit as x approaches negative infinity of f of x is equal to L, then the line y equal to L is a horizontal asymptote. So let's say we have a graph like this, and it goes something like this, and then it just like approaches some value over here. So this is going to be the horizontal asymptote at y equals L over here. And let's say that at negative infinity also approaches negative L. So this line would also be y equals L. And as you see, it approaches it but doesn't reach it. But it is around the line y equals L. So let's continue on from this. A function can have up to 2 possible horizontal asymptotes, one from the left and one from the right. So one is x approaches positive infinity and one is x approaches negative infinity. They don't necessarily have to be the same value. Horizontal asymptotes can be crossed at any point on the graph as they only detail the end behavior of a function. So although a function may like approach 3, y equals 3 over here, and then like y equals 4 over here, it can still cross the lines. It's just that these are the values that the function approaches as x becomes really big. So over here we have the function f of x is equal to x over x squared minus 4. As we can see here, the horizontal asymptote is 0 because the function approaches 0. It doesn't reach it, but it gets really close to it. So as x goes to infinity, f of x will approach 0, and as f of x approaches negative infinity, f of x is going to equal to 0. So as x approaches negative infinity, f of x is going to approach 0. And over here, you see that the graph crosses the horizontal line, which supports what was said over here. So imagine we have a function. If a function has a constant in the numerator and a variable in the denominator, then as the variable approaches infinity, the function approaches 0, where c represents any real number and n is a positive rational exponent. So let's say we have the limit as x approaches infinity, c over x to the power n, well that's going to be equal to 0, and the limit as x approaches negative infinity of c over x to the power n. The reason why this happens, let's say c is equal to 5 and that x is to the power of 3. So as you approach infinity, 5 is going to stay the same, but x is going to approach infinity. So 5 divided by a very, very big number is going to approach 0. So let's say we have like 5 over 100,000. That will be like 0.005, something like this, or one more 0. So as x gets bigger and bigger, you're dividing 5 by a larger and larger number, which means that it will eventually approach 0. So now for this third example, we're going to find the limit of f of x as x approaches infinity. So we have f of x is equal to 5 over x squared, and we're trying to find the limit as x approaches infinity of 5 over x squared. So basically, from this other slide, we have a constant on top and a variable on the denominator, which means that this is going to approach 0 because 5 over infinity squared is just going to be 5 over a very, very big number. So this is just going to be 0 because any constant number that does not change over a very big number, let's say it's like 9999999. So 5 over 9999999 will approach 0 because you have a decimal that looks like 0.000000 repeating 5, something like this. So this is an infinite amount of zeros. You can say that the value approaches 0 because there's a tiny number divided by a huge number. So that will approach 0. Okay, so now let's talk about horizontal asymptotes of a rational function. So we're going to use comparison of degrees and leading coefficients to determine the horizontal asymptotes. So you have a rational function composed of two polynomials with leading terms of ax to the power n over bx to the power m. Then based on the limit as x approaches infinity of ax to the power n plus whatever other terms with lesser degrees are included, then the following is true. If the degree of the top is less than the degree of the bottom, then the limit is going to be equal to 0 because you're going to have a lesser number over here being divided by a huge number, which means that's going to eventually approach 0. And then for the second one, if the degree is the same, then basically when you approach a huge number like infinity, the other terms won't matter because they have lesser degrees. So in comparison to the larger degree, the other term is considered negligible. So you're basically going to have, let's say, axn over bxn because these two are the same. These can cancel out, and you have the ratio a over b. And lastly, if n is greater than m, then the limit is either positive or negative infinity based on what sign the leading coefficients are. The reason why this is because you have a bigger number over a tiny number, which means that you're still left with a big number. In other words, if the degree on top is less than the degree on the bottom, then the limit equals 0. If the degree on top is equal to the degree on the bottom, then the limit equals the ratio of the leading coefficients. If the degree on top is greater than the degree on the bottom, then the limit does not exist, where it decreases or decreases without bound, also known as negative or positive infinity, meaning that there is no finite number for the limit, or like there's no clearly defined number that the limit can be equal to. So that's why the symbols infinity are used. Overall, the highest degree term has the most influence in determining the end behavior of a function. Okay, so these are the wrap-up notes. Rational functions always approach the same horizontal asymptote from the right and to the left if it has a horizontal asymptote. Functions that are not rational, such as radical, trigonometric, exponential, and logarithmic, may approach different horizontal asymptotes to the right and to the left. Not every function has a horizontal asymptote. Horizontal asymptotes only describe end behavior and can still be crossed by the graph. Rational function shortcut compare degrees and leading coefficients of numerator and denominator. Limits at infinity are often used to see what value a function approaches as its input approaches infinity. For example, a population function. Okay, so this is going to be the end of today's video. I hope you enjoyed watching, and I hope you learned something new. Goodbye.